In this lecture, we're going to go back to the SN2 reaction and talk about how the reaction works and start to dig into the mechanism for the reaction. So if you recall, when we were talking about free radical halogenation, I said important details to understand as you're studying a new reaction are the mechanism of the reaction so that you can effectively be able to predict the products for the reaction. So let's go back to the reaction. Let's put a new reaction in front of us. So if we had, for example, this reaction, and instead of me giving you all components, I'm going to leave out the products. So products are not included. And what we want to be able to do is predict the outcome for this reaction, predict the products for the reaction. So if you hang on just a second, I am going to ask my, sorry, I had to ask my kids to go back downstairs. Okay, so back to it. So we want to break down this reaction into the mechanism so that we can effectively predict what the products are. So first of all, what we should do is label the components of the reaction. The haloalkane is going to be the electrophile for the reaction. And then the thing with the, that's usually a salt, has a lone pair of electrons. The thing that's reacting with the haloalkane, that's our nucleophile. And we should recognize that it is a salt. And so what we want to do is sort of cross out that potassium atom and replace it with a negative charge. Now, what this reaction ultimately takes advantage of is that the haloalkane has there's a large difference in electronegativity between the carbon and the bromine atom. So we have a significantly polarized covalent bond. That is to say, if I redraw this, just to make it a little bit bigger, we should recognize that we have a delta minus and a delta plus, and we could draw the little dipole arrow. We have a permanent dipole between the carbon and the bromine atom. And so, as a result, if this oxygen atom that is desperate to react with anything with a positive charge can engage the molecule, it's going to react with the delta plus, right? It's not going to be attracted to the delta minus on the bromine atom. It's going to be engaging the delta plus. Now what that's going to do is that attraction is actually going to force the breaking of the carbon-bromine bond, as that bromine is already siphoning away the electron density towards itself in a polar covalent bond. It's going to go ahead and suck all of the covalent bond electron density, and that's going to give us the formation of a new bond between this atom, which I'll highlight as a dot, and I'm going to draw that new bond in green. And we're going to form a bond with that and the oxygen atom of the nucleophile, and we get to a molecule like this. Now, as a result, the Br minus floats away because it is the leaving group. And leaving groups leave. This time it was shoved off by the nucleophile. The nucleophile engaged the delta plus carbon, pushed off the leaving group, and that gave rise to the formation of a new bond. Okay, now what we want to do is redraw our product so that it looks a little bit more aesthetically pleasing. Now, if we do that, we have 1, 2, 3, 4, 5, 6, 7 atom long chain, where at atom 4 is our oxygen atom. Okay, and then at carbon 5, we've got an additional methyl group. So this is the desired product. We formed a new bond between the oxygen and the dotted atom. And that new bond I'll highlight in green. Okay, what we've done here in this is predict the product for the reaction. And if we wanted to, we could have the bromine find what did we start with? Potassium finds the K plus to give KBr if we want to, but that's not something we have to worry about too much. We don't have to worry about that too much. It's the desired product that matters here. So the desired product is that the molecule that has a bunch of carbon atoms present, that gives rise to the product with the new covalent bond. And I just took it and redrew it in such a way that things sort of looked aesthetically pleasing. But hopefully you can see when I first drew this product, I'll just do this temporarily. I just kind of positioned this nucleophile above the interacting atom so that I could see the new bond that was formed, right? So this is just the nucleophile interacting with that atom with a dot. Okay, so that is the SN2 reaction, its mechanism, and how we use that mechanism to understand what products are being formed. Now, what I can't really emphasize enough is we want to know the mechanism to be able to effectively predict products. Now, what I should do is draw generally what using the Rx and the nuke minus, I'll draw those frameworks so that you can see what the mechanism generally is on the following page. I guess I could do it right here. I can fit this. Okay, so Rx, we have a delta plus on the R, we have a delta minus on the X. That's going to interact with nuke minus. I'm going to take my curly arrow and start it at the negative charge, come around, attack the R group, and push the electrons over to the X atom. The R is a carbon atom that can only have 4 things attached to it. In the starting haloalkane, it already has 4 things attached to it. So when the nucleophile comes and adds, it's going to be overwhelmed with 5 things. It needs to immediately lose some electrons to make room for the new covalent bond. So it's going to lose the covalent bond electrons between it, the carbon atom, and the leaving group. So the leaving group is going to be sort of pushed off as a result. So we have our, I don't know how to do this. We have our central, imagine these 2 atoms are bonded, but then the, let's see, I'm not going to do this right. I don't have a good analogy. Sorry. It just kind of comes in, pops off the X group, makes a bond between the nucleophile and the R, and the X walks away as a negative charge. That's the mechanism. I wish I hadn't drawn it so small, but hopefully you can at least get the idea. The nucleophile with a negative charge adds to the carbon, simultaneously pushes off the X group to give rise to a new bond between the nucleophile and the R group. That's the overall mechanism for the reaction. So it's a lot simpler than the free radical halogenation reaction. And what it ultimately stems from is the fact that carbon being bonded to bromine has a difference in electronegativity and exists with a delta plus on the carbon atom. Exists with a delta plus in the carbon atom. Sorry, I'm jiggling here, I guess. And what happens then is, since it has a delta plus, it will attract the negative charge in the nucleophile, and that's what encourages the formation of the bond and the breaking of the leaving group. So with that, we'll end this lecture.